Hi, and welcome to the MCubed 2019, and welcome to our talk, 18,000 Signals, an Average Day for an Automotive Engineer. We want to show you the data we have. It's time series data, full CAN traces with 18,000 signals and more than 100 data points per second. And we collect them, we store them, we work with them, and we want to show you the best practices and machine learning algorithms we use to work with those data. Really love data, and why we and because of we really love data. Data is like our pets, and as you may read in our abstract of this talk, we compare data with pets, and we want to keep this picture for the whole talk. So let me introduce myself. My name is Fabian Bormann. I studied computer science at the University of Lübeck with a minor in neuro and bioinformatics. And after that, or during my master, I worked for the Fraunhofer Research Institution for Marine Biotechnology and Cell Technology. And after that, I moved to IAV and work now with automotive data, but also with machine learning. I work as a data scientist and data engineer for IAV and doing my PhD besides of my work now at the University of Lübeck.
Yeah, and welcome from me. My name is Sara Bertram, and I'm also working for IAV in Germany as a software engineer and data analyst. I studied software engineering in my bachelor and computer science in my master on the University of Lübeck as well, but even if we've been there for the same time, we didn't meet each other and only met at the IAV.
Oh yeah, I think that's my fault because I was not too often at the lecture.
So we want to give you a short introduction about IAV, and because you may not, you are not so familiar with automotive engineering. So IAV is an automotive engineering partner. We work for like every OEM in Germany, for Volkswagen, BMW, Daimler, and so on. In our location, that is Gifhorn in Germany. I think you will not know this city, but
of course you not know the city.
We are over 4,000 people, and we have offices worldwide. So it's not that small company, but because we don't work for end customers, you did not know IAV. We have three main sections: the powertrain development, the vehicle development, and the digitalization. On the left side, you can see the main points. What we're working on in our section is like an interface between the software world and the automotive world, because we work together with automotive engineers and bring data logger into the cars. So we have a lot of data we collect every day, and we store that data in our own measurement data platform, like in just a normal database, and this for over 15 years. So we have a lot of experience with that, and we do a lot of analyzing with the data. So we do that to give our customers an advice if the new car component, the new control unit matches the testing results, and if they can put them in the new car. So that's really important. And that's where we originally came from. But now time changes, and we do a lot of more data science, data engineering, and the machine learning stuff. Because we work with big data every day, we need to test and to check out new methods and new machine learning methods in data science and data engineering. And that's what we want to show you today.
Yeah. So we want to show you how to work with our pets, and we have a few of them here in this picture. But before we speak of what's the difference between those pets, we want to look what they all have in common, and want to show or give you some general pet maintaining approach. First of all, you go to a pet store and you collect your pet, and after that, you may need to pre-process your pet by a doctor because it's not in the right shape or something like that. And after that, you ingest the pet into your home, and then came into the really cool part. You play with your pet, you keep track, you analyze the behavior of your pet, and then you go and get awards on pet contests or talk about your pets at any conference. And we use machine learning frameworks, of course, from an open source ecosystem. So we mainly use Keras for prototyping on top of TensorFlow. And we heard it in the talk before, we use PyTorch in production. And I want to talk a little more deeper about PyTorch tomorrow. And we also use CNTK for time series, but CNTK, you might hear that, is not developed actively anymore. But Sara is talking about that tomorrow because she is give a little framework time travel tomorrow. And but we also use CAFE if we work together with universities, because universities, I don't know why, are very love CAFE. So we use CAFE, but we also use OpenCV and load the CAFE blobs. So yeah, it's a little bit hacky maybe, but because of we do our stuff for 15 years now. We have very huge amount of applications written in Java, and that's why we also use deep learning for J, because it plugs in very cool. But I know all of you, I think the most of you, want to do the cool stuff, the play, keep track, analyze, get awards. I want to do the same, but sometimes I hear two sentences. The one is machine learning is all about the algorithms, and the other is machine learning, it's all about the data. So maybe room indicator with hand sign. What do you think? Is machine learning all about the algorithms? Is machine learning all about the data? Okay, it seems that you have worked with machine learning before. So yeah, it's because the algorithms are based on data, and that's why this section or this part in the below part of the image is really important. The important part is how to collect the data or the pet correctly, how to pre-process it so that you can work with it, or how to ingest it. And we work with a huge amount of tools you see right down on this slide. We use Kubernetes and so on, but tools and frameworks are changing, and that's why we want to give you an building block approach. So yeah, when we build our platform, we switch the tools, but the building blocks are always the same. So most of the people thinks that we in automotive industry work with stream processing a lot, because yeah, the car drives around and then streams the data very fancy to us, but yeah, sadly it's more batch processing, because this huge amount of the data. Yeah, we have 18,000 signal on the CAN bus, and all were collected, and then we have more than 100 signals or data points per second, and the test driver is drive for 2 hours or even more. And so the test driver stores the data during his drive on a hard disk, and then he gave us the hard disk. So that's why we work with batch processing and today. So we use stream processing, of course, during the ingestion to have some events. What we store for metadata is really important if you work with time series data, or you want to reuse the data later for other projects. Yeah, we learned from failures. So metadata is really important, and that's why we use data flows, and for that we use Airflow mainly, which is a framework where you can use, which is a programmatically approach to let your data flow. You have some scripts and you can schedule it, and you can do some event-driven stuff. And that's really cool, and we love Airflow, but sometimes we also use NiFi. I don't know if you used NiFi before, but it's very nice because you have an user interface and you have some kinds of processors, and you drop down the read from SQL database processor, and then you transform the data with processors, and then you have an output. And the nice thing when you use NiFi is you can show it your manager, because often managers do not want to see your code. They want to see flows or something that shows the managers it works. And NiFi does that. So we transform the data often in Parquet or ORC. It's very important too, because if we work with 18,000 signals and we have a question where we ask the system, gave us the all the data in our database where the vehicle speed is greater than 150 kilometers per hour. Then if you would store the data in a row-based file format or database, you need to touch every signal, and that's kind of hard. If you store it in a column database format, then and use Spark or something like that, which is lazy, then you can easily only use the vehicle speed column, and that's speed up the thing much. So for resource management and scheduling, we use, of course, Zookeeper in our Hadoop ecosystem. On our test cluster, we have 11 nodes, I think, and all of them have frameworks on it, and there we use Zookeeper or OpenShift, which is the Red Hat Kubernetes distribution, or vanilla Kubernetes. So I don't know if this is interesting for you, but we have often the problem that the data governance is really important, because we work with different OEMs. So Volkswagen don't want that BMW see their data, of course. And that's why we need to have a special data governance layer. And Keycloak is very cool because you can easily plug in into your ecosystem. This means your direct access or LDAP or something like that. It works with your cards if you have cards to log in or something like that. So it's really cool. And Keycloak secures your applications you wrote on your own. So if you wrote a web interface or something like that, you can use Keycloak for the login interface. Okay, so we need this to keep our data quality good. And so we use Spark for the processing, for the distributed processing on our data, and we have an MongoDB for our data warehouse where we have some unstructured data. And of course, we use Jupyter as well. A little story. I was at Google for the Google Summer of Code, and there I talked with one guy from the Jupyter organization, and he told me, oh man, this name is so hard, because we looked for a name and there was Jupyter. Jupyter is so cool because it's NumPy, or from Python, IPython notebook where we originally came from, but everybody says Jupyter. So, and I think now everyone says Jupyter, and even Jupyter says Jupyter. So Jupyter is one. But we also use U, and U is a really cool notebook because you can change the kernel in each cell. And U is more than a notebook, it's more than a workbench, because you have also a file view on your files, on your data directly, and you have also a database plugin where you can fire up quickly any question. So, and now the interesting part of it, now we want to do some data science with our pets, and we want to show you the pets we often used and the algorithms which we used in our projects, because we act as an automotive supplier. We have projects. We cannot just do some research, sadly, but we do some research for special use cases for projects, and that we want to show you.
Yeah, at first we have our audio cat here, and of course we work with speech to text. We even put it in the car and do a lot of dialogue speech in the car. We have a project called Empathic Assistant, so talking to the car in the car. We also have worked with hot word detection. So if you imagine a test driver is doing a very important test drive and he sees something strange, anything he wants to notice, so he can say hot word, that is like a trigger, and we save that and put it to our data or measurement. As well, we work with speaker recognition, like the same use case, so maybe some more drivers in a test car, and they recognize something, they say something, and we recognize the speaker and just can write it in the perfect database or perfect space for that node. The last point is noise and environment detection. So if you imagine you're driving your car and you can just, because of the noise and the environment, we can find out if you're driving in the city or on the highway or something in the landscape. So that's the important point.
And if we work with image, of course, we work with semantic segmentation. This means FCN or dconfnet or Bayesian signet or something like that. We use this as a pre-process step for autonomous driving, and but we also have projects where we need just to detect some objects. We have a project with the University of Berlin called Safari in the last year, and they have a map of Berlin, and they want to keep that map up to date. So they are interested in construction places, and they want to keep the map up to date with dashcam data from the car. So that is a thing where we use YOLO or something like that, and we have also style transformations. As we have a test drive, then we want maybe to change the weather conditions on this test drive. And on top of it, we also have generative algorithms. We was at the CES this year or last year, I don't know, in Vegas, and there we showed a system to pseudomize people with generating faces and replace their faces in images, just because we often have videos we want to show, test drives we want to show, and if you just blur the people out, then you destroy the image in a way. So
yeah, and we have the text pad. So we do a sentiment analysis. We have a project where we have a chatbot in the car, and you can speak to the chatbot and say something like, I want to buy a new blue jeans, and the chatbot or the project will add the blue jeans to your grocery or to your shopping list and will guide you to the next shop. As well as we work with content generation, you all know ticket system Jira, or we have for other projects where we have like hot word detection and combination, and we can generate automatically any error tickets or something like that. Translation, you all know Google Translator, and we are more fan of DeepL. That's a machine learning based translator engine, and we think it's like even better than the Google Translator. And we work with Word or doc to vector, so we have type of syslogs or any other log data from our car components that we can compare and find any outliners in there. So the really syslog you don't want to read by yourself.
And of course, the classic machine learning, we have features, and we want to do some decisions on it or want to know which is the most important feature. And we also do classification stuff, or where we came from is parameter tuning of engines. We have an engine, and that engine should also perform under other weather conditions, and then we need to tune the parameters, and the colleagues of us use machine learning techniques, I think since the 90s or something like that. And yeah, but we have time series, or we have pets with special needs. This is our time series data. And the most common things you do with time series data is anomaly detection or outlier detection. You do some pattern detection or just forecasting it. But we want to do based on the time series a decision making. We want to have the feature importance. Of course, if we have 18,000 signals, we want to know which signal is the most important, or which are the most important signals, without asking a car engineer every time. And we want to do some classification based on that. And we do not have univariate time series. Yeah, we have multivariate time series. So we have real-world challenges with our data. This means sometimes we have hidden information. If you have a logger in your car, then you need to configure it so that it measures all the data from all the units you have in your car. So the problem is sometimes the logger is misconfigured or was misconfigured, and you do not have the signal. Or you have missing parts because of initial values where the logger is not ready yet, or the data is just missing in your time series. You have a different look and feel. This means you have two signals. They should be the same, but they are not the same. So this are our real-world challenges, and now it comes to the point where our boss came in and comes from a customer or something like that and brings a concrete task with him.
Yeah, and I want to show you how we put all of this together. So what you can see here is a screenshot from the infotainment console of any car. So imagine that. And we built an in-car app store. So like the thing on your smartphone, we built an app store for your car. And by now we have these two apps on the left side, the Lights app and the AI assistant. First, I want to show you the Lights app. So modern cars often have the drive mode selection. That's what you see on the right side. We have the, for example, the eco mode, the normal mode, or the sport mode. So when you drive, you can select, oh, today I feel a little bit sporty, I want to drive in the sport mode, and the engine and something like that behaves a little bit different. So in the Light app, you can set the ambient light depending on the drive mode you selected. So maybe the normal mode is blue and the sport mode is red. So whenever you drive in the sport mode, the ambient light on the doors and wherever your car has it will be red. So that's the easy part. And now we come to the AI assistant. It's also based on the driving mode, but a little bit complicated and machine learning inspired. So we collect all the data, all the measurement data from the data logger in our cars, and we analyze it. And with feature prioritization and feature detecting, we find out whenever the drive mode is changing. So we took the point where the drive mode is changing and look at all the signals at the same time. And then we can predict the drive mode in any other situation. So a very easy example that you can imagine, you're driving on the highway and the signals are like driving on the highway, and the next time you're driving on the highway, the AI assistant noticed that and thinks, oh, last time there was a sport mode, maybe I predict the sport mode today. And then you get a pop-up on your infotainment console which asks, oh, do you want to drive in sport mode? And you can say yes or no, and feed the algorithm with your decision. So whenever you click yes or no, there's a new train data collected and sent to the backend, and is used for another round of training. As well as we use it for in-car training, so the algorithm adapts to the driver, and when you click every time on the Autobahn, for example, or the highway, yes, sport mode, yes, sport mode, it will be better and predict sport mode even often. So, and what's all behind that? Fabian is showing you now.
Yeah. Now we have a general approach to solve problems like that with our data. Our data is, yeah, I say it for all of our customers, so it's okay. Our data is crap. So we have signal names which look like this. My favorite is the smiley on the top. So we never know what is the meaning of this signal. So we have special signs in every signal, and this results in a syntax error every time if we work with Python, because I don't know if they do this with any special meaning, but they use the special signs in a way that is really tricky. So you need a data definition file if you work with car data. This means if you have a logger and you use the logger in your car, then to get the full CAN, then you get a binary blob out of it. And now you need the data definition file from the original manufacturer to interpret those data. If you do not have this file, you have a huge binary blob, but nothing in it. So if you have this file, you get most common an MDF file out of it. MDF is a format we use in the automotive industry a lot. And you cannot use MDF in Python directly. I think for the last 2 years or 3 years, there was upcoming a few libraries, AMSAF MDF or something like that, which allows you to read MDF3, and I don't know if MDF4, but you cannot read it in a distributed way because you cannot use it in Spark. And but there's a trick I want to show you. And we wrote this this framework for analyze time series data for 10 years. It's called Ameda. Ameda is a Java-based library for automotive, doing some automotive analysis. And because of it's Java-based, we can say to Spark, hey, I want to use a special input format. And then we tell Spark we have an Ameda file. But there is no Ameda file, there's just our framework, it's Ameda. And Ameda is reading an MDF file and do some transformation with it, clean the data, backward filling, forward filling if there's any missing data and so on. And if Ameda is finished, Spark thinks it finished reading the Ameda file, and now we have the MDF as a Spark data frame in our Hadoop ecosystem. That's pretty cool. After that, if we have the data, we need to find the needle in a haystack, because we have those 18,000 signals, and we don't want to use those 18,000 signals. We just want to use the top 20 signals for this use case. And that's the point where we came to, we need to use something like random forest or something like that to get the feature importance. So if you remember random forest, it's a machine learning algorithm. I think it's from the 90s, or it's old-fashioned machine learning, but it's really cool. So you have your data, and in our case, we build slices. We wait if the driver changes the mode, and then we did slice the time series and build some features up on the time series, like the variance or the mean or maximum and something like that. And we have the label, driver changes the mode, driver did not change the mode, and something like that. And then we have those data, and the random forest take the data and collects the data into a new data data matrix, and but allows duplicates. So we have a new data matrix with a few data, and we generate a tree out of it, and then we use this features, or random forest use this features which allows the tree to reduce the entropy a lot. This means if you have bananas and apples, so fruits, and you have the features color and the features size, then your bananas are yellow, your apples are red. And if you use the size lower than 30 centimeters or something like that, it could be that there are also apples and bananas on the left side and apples and bananas on the right side. But if you use the feature color is yellow, then you have bananas on the right side, apples on the left side, the entropy is 0, and this is a really good feature. So random forest generates a lot of the data, so it generates a lot of data with duplicates and so on. It builds random trees, and so random forest, and we don't use this for classification, we use this for feature importance, and it worked very good. But we found out that gradient boosting together with shape values worked even better. Because gradient boosting, this is also a decision tree algorithm similar to adder boosting, but adder boosting builds just stumps. Gradient boosting builds small trees and learn from the error of the previous tree. And this is really cool. And if you use shape values, which are inspired by game theory, then you can use them to get the best features with the best, highest feature importance. So that's the way we build up our feature store, because of, we don't want to ask our car engineers, hey, could you look at these 18,000 signals, please? One of them is a smiley. So this is the whole chain. We have full CAN traces, we generate the feature store with it, we have different algorithms run on it, random forest, of course gradient boosting, we had used this before. We have recurrent neural networks like LSTM or gated recurrent units. We also use convolutional neural network and some logic if we want to predict the light in the car, if it's should be turn on the adaptive light, then it maybe does not sense in the day. So, and then we decide to take the outputs of the algorithm, which are trained at the back end, to give the output to an MLP, which is trained in the car. So, so the MLP is doing some, there's some ensemble stuff and gives a final prediction, and the driver gets the prediction, like Sara mentioned, with the dialogue, and then he could accept or deny it, and or choose another driving mode. And we use this to generate new train data, and also we use this to generate train data for our measurement database, and then we can run the next version out of our algorithm, new feature prioritization on the new data, and so on and so on. And then we came to the interesting stuff where we do some parameter tuning and over. So after the validation, we found out, oh, the model is really crap, because our data was from endurance testing. And endurance testing means we let the cars drive until they are dead in a circle. And the problem is none of our end customer is really drive his car that way. So we need to get back to the pet store and get new pets, and then start the pre-processing and do the whole chain again over and over until we have a really good model. To get the model is like building a house. I would not use the first model for myself. So if you ask yourself now, okay, how do they get the data slices in a fast way? Because we do this every day, and if you use every day a notebook or something like that, or a code snippet to extract this data slices, then it comes to the day where you think yourself, oh, a graphical user interface and a quick way to see if the data matches could be really useful.
Yeah, and this is where our AIV measurement data platform comes handy. So we built the interactive data analytics part of it, which you can see here. Yeah, we have like over 800,000 kilometers measurement data, so that's really a lot. We have a lot of cars, a lot of fleets.
In 1 year.
Yeah, and we would like to have a search engine like Google, which is really fast and can find our data really quick. So we built this interactive data analytics. We do not only collect the signals and the car, but we also collect some metadata. For example, the fleet, the car, the firmware of the control unit, or the location. So on the bottom you can see the geoposition, so we collect GPS data as well. Yeah, and then you can search for any signal you want. So on the right top, it's in German of course, but it says a speed over 80 kilometers per hour and acceleration over 1g. So you have an easy SQL-like syntax here, and you can just connect single search parameters here. And after you click on the search button, you will go to this result page. And on the left top, you can see all the events found with this search parameters. So you can see there are over 9,000 events found in all our measurements. That's obvious because speed over 80 is not very uncommon. And on the bottom you see the signals. So we have the two signals here, speed and acceleration. And now we can search for some outliners, for some very special things found in our measurement, and search for them especially. So click one. Yeah. So we can jump into our data and pick a timestamp where you think, oh, that's crazy, that should not be this one, whatever. And you can search for this and check if it's just an outliner or if it's normal or if it's a part of the firmware or whenever it happens, and find out yeah, what's crazy about your pattern.
We did those pattern detection stuff also with machine learning. Before a few years it was that we do it manually. This means if our customers came and say, do you have, I have a pattern here, how often is this pattern in my data? So we sit down and then we write down the pattern description. This means the velocity was first under 20 and then in the next 5 seconds it could be that it, and this was really hard and takes a lot of time. And so we used LSTMs or convolutional neural networks or even some statistics to get directly an output of pattern in and pattern out. And then we go to our customers and say, here, this is our crazy machine learning algorithm, and our customer says, okay, I have those 21 pattern, but you found only 20. Why do you don't found this pattern? And then it came to the situation which you may really had too. So I said, it could be that it's a black box algorithm, and I don't know, maybe it was not in the train data or something like that. And yeah, we learned from it, and we went a step back, and now we use machine learning to generate the pattern description, which does the same. We click on search, and then we search with the pattern, with the generated pattern description, and end to end, there's nothing changed. But if the customer comes and says, hey, there's a problem, I didn't found this pattern, then we can look at the pattern description, adjust it, says, okay, here is no support point, I did a support point, or here's a support point, but this needs to be a much higher tolerance value or time tolerance or something like that. And then we can also find the missing pattern. Yeah, thanks for your attention, and questions are really welcome if there is time. Thank you.